Welcome
Welcome
everyone.
everyone, 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 everyone.
Hi everyone,
Hey everyone, hey
welcome.
everyone, hey everyone, hey everyone.
All right, can you hear me okay?
Can you
There's
hear
a
me okay? Hear
phone.
me okay? Hear 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 me okay?
Is that better? Okay. Sorry about that. All right, everyone, welcome to Fine-Tuning Fairness, Curating Datasets to Eliminate Gender Bias in Technical LLMs. Before we begin the session, we wanted to remind everyone in the lobby to click the join button below or next to the session to be able to access the session chat and utilize the Q&A function. Uh, to submit your questions to the speakers. As well, check out our expo area during the event for an hour after the event concludes, and learn about the amazing work our exhibitors are doing. Can you all hear? Sorry, give me 1 second. There's some feedback. Okay, there we go. So here we have Zarya Halliger, who is an AI engineer focused on the ethical deployment of machine learning. From fine-tuning LLMs on specialized documentation to architecting semantic shields for digital safety, Zarya's work prioritizes model reliability and inclusive engineering. She is currently exploring the frontiers of NLP and bias mitigation to ensure AI serves as a tool for universal empowerment. So I'm going to go ahead and turn it over to Zarya. Thank you so much for being here with us.
Thank you for having me. Hello, everyone. My name is Zaria. I am an AI engineer who specializes in fine tuning and bias mitigation in large language models. What I want to talk about today is a problem that most of you have probably already bumped into, even if you haven't had a name for it yet. It's the way technical LLMs quietly default to gendered options. And most importantly, what it actually takes at the data and training level to fix that. Can everyone see my screen? Okay. All right. Let me just here. In 2017, Amazon's engineers found something uncomfortable about a recruitment tool that they were building for a few years. It had been trained on 10 years of resumes, so it became a data set that just by reflecting who'd been hired in tech skewed heavily male. So the model learned resumes that look like past hires score higher. It started penalizing the word women's, even in phrases like women's chess club captain. It downgraded graduates from all women's colleges. Nobody told it to do that. It learned to. Amazon scraped it before it could ever become a model that was used. It became one of the clearest documented examples we have of bias being baked in through data. That was in 2017. What about what's on your laptop right now? Audits of GitHub Copilot found it defaults to male pronouns for engineered roles at a noticeably higher rate than neutral alternatives. GPT studies found the flip side, female pronouns by default for nursing, caregiving, and admin roles. This isn't one product's bug. It's the same systematic fingerprint everywhere a model trains on uncorrected human text. Researchers built a whole benchmark for it called 1.0 bias. We'll come back to that a bit later. This is what we'll be going over today. Part 1 is going to be how bias gets into a model and how to measure it. Part 2 is the full technical pipeline from data augmentation to synthetic generation to LoRA fine-tuning. Part 3 is going to be our final evaluation and deployment gates. Let's get started with where things go wrong. Models learn the internet's habits, not its facts. Stack Overflow's contributor base is 92% male. GitHub code comments lean masculine at similar rates. The model doesn't just absorb that ratio, it amplifies it. A 92-8 skew in the training data doesn't produce a 92-8 output. Association learning compresses it until the model treats it almost like certainty. In case we have some non-technical folks in the chat, I created a quick glossary of some terms that will pop up that might confuse a few. We have LLM, which is a language learning model, predicts the next word. Its knowledge is a statistical pattern and not a fact. I'm going to copy and paste these into the chat if you guys want to refer to these whenever you get confused or need a little help. There we go. And that way you can refer back to them in case you need them. Or feel free to take a screenshot as well. Before you fine-tune anything, sample your corpus and run a pronoun ratio check. A balanced corpus lands close to 50-50. We flag anything more than 15 points off priority. Here's what that looks like on a real tech corpus. A 0.74 he against 0.26 she. That's a 24-point gap. The script flags it automatically. One number isn't enough. We need a fuller picture. So we have bias ratio. Our baseline code came in at 4.2. Male pronouns outnumber female pronouns more than 4-1. Pronoun default rate, which is what the model reaches for unprompted, 0.87 masculine at a baseline. Occupational skew, which is whether the model links specific roles to specific genders. Here we have 71%, which is above our 55% target. Then we have our counterfactual gap, which if you swap he for she in otherwise identical prompts, does the output change? Ideally, that gap should be 0. Our baseline is 0.31. Google's People in AI research team puts it simply: don't treat fairness as a final audit step. Design for it from day one. In practice, that means 3 things. Define your fairness criteria before you write training code. Instrumenting your pipeline to surface bias at every stage. And treating debiasing as a real engineering task with tickets, owners, and SLOs, not a one-off cleanup. Three points I want each one to land before I can move on. 1.0 bias found off-shelf models defaulted to stereotyped answers on ambiguous sentences up to 90% of the time. The Fair Coder study found masculine pronouns defaulted to 73% of generated doc strings, even for completely role-neutral tasks like sort functions. In a 2024 UNESCO report, tied biased hiring AI to measurable salary disparities in organizations that deploy without a fairness audit. This is published, it's peer review, and it's also the foundation for everything we're going to build in the next few minutes. Now we build the solution in section 2. Text gets tokenized, split into chunks, and each mapped to a new number. Those become embeddings, where related concepts cluster together. Transformer attention layers compute relationships across every token and context. The final layer outputs a probability for every possible next token. Bias lives at every one of those stages, but it concentrates on the embedding space where demographic associations get baked in and get amplified through attention before it ever hits the output. 3 words I'm going to keep using throughout this section are going to be tokens, parameters, and distributions. This is our map for the rest of part 2. We have our raw corpus, we have audit, distillation and augmentation, fine-tuning, evaluation, and deployment. Fairness isn't one action, it's a pipeline with a checkpoint at every stage. Skip any one of them, and you get a model that passes a compatibility test but still fails your users. More data is not better data. Data distillation uses a larger teacher model to score examples from our raw corpus. You keep the high quality, low bias ones for fine-tuning our student model. Here's the funnel you see on the screen. We go from 10 million raw documents to 6 million after deduplication, to 2 million after quality filtering, to 950,000 after bias filtering. That 950,000 curated set can match or beat the original 10 million while cutting down bias metrics to 40 to 60%. We're not losing capability. We're cutting the noise that's teaching the model the wrong lessons. For every gendered example in your training set, CDA generates a mirrored version with pronouns swapped, and you train on both. For example, the engineer solved the bug. He committed the fix at 3 a.m. That gets a counterpart, same sentence. She committed the fix. At scale, this teaches the model that the task quality has nothing to do with demographic signal. Good. Okay. When your real data is too skewed to rebalance by filtering alone, generate synthetic examples. Use a frontier model with a fixed template. Swap roles and pronoun slots systematically, and you get a balanced set at scale. Synthetic data needs its own quality gates, a fluency filter, a check that no demographic term leaks into the task output, and human spot checks on random samples. Generating 5 to 10K examples that are balanced typically runs you about $20 to $80 in API fees, which is a strong return for the fairness impact we're creating. PEFT, or parameter efficient fine-tuning, means updating a small slice of a model's weights, not all of them. Think of it as a tune-up, not an engine rebuild. LoRA is the specific technique we'll be using. Instead of updating a weights full matrix, you add two small matrices whose product approximates the change you want. Rewrite the sticky notes, not the whole textbook. Why it matters in fairness work is because most teams can't afford to fully retrain to fix pronoun bias, but they can afford this. This is about 95 to 99% fewer trainable parameters, training on a single GPU in hours, and the base model's weights never gets touched. R16 is the rank, how expressive the adapter is. 16 is the sweet spot, enough to change the behavior, but small enough to train fast. LoRA alpha 32 is a scaling factor. Doubling the rank is a common rule of thumb. Target modules point to qproj and vproj. The query and value attention projections, which carry most of the semantic association we're correcting. And at the bottom line, we have trainable 0.0622. We're updating 600ths instead of 1% of the model's parameters. A full fine-tune will cost roughly a couple thousand more to compute. Supervised fine-tuning trains on instruction output pairs. For fairness work, every output in that set has to demonstrate the behavior you want. Gender neutral, assumption-free, and task focused. The loss function is standard cross entropy, computed only on the output tokens with the instruction mask. The model is just learning to maximize the probability of the target's tokens. But if even 10% of our training examples slip through with biased outputs, the model will eventually relearn the bias right alongside everything else. So data quality isn't optional here. It's the whole mechanism. Standard fine-tuning loss only rewards correct outputs. Counterfactual loss adds a penalty whenever the model treats demographically swapped inputs differently. We measure that gap with KL divergence, a way of quantifying how far apart two probability distributions are. If a model is genuinely fair, he is the engineer and she is the engineer, should produce nearly identical output distributions. Any gap becomes part of the loss. Alpha controls the trade-off. At 0.1, fairness barely moves. At 0.7, compatibility downgrades. At 0.3 is the balance setting. And at that value, the counterfactual gap drops from 0.31 to around 0.04, with less than 1% hit to the general capability. Excuse me. Same output, both models. Write a function that assigns a code reviewer to a pull request. The baseline writes, he will review the PR and greets the reviewer, hey man. The fine-tune model just says new PR signed for review, uses a type hint, and picks the reviewer based on queue length instead of seniority, which is also just better overall logic. Now that we've went through building the pipeline, we're going to prove that it works with part 3. We need to measure 3 things simultaneously, and all 3 have to hold. We have to measure our capability, which is MMLU delta within 2%, human eval within 3%, and latency overhead under 2%. Our fairness will be measured with 1.0 bias, score under 0.10, pronoun default rate to under 0.55, and our counterfactual gap under 0.05. Robustness is our adversarial pass rate, has to be above 90%. Plus, we also have to have a human review panel with at least 80% agreement. A model that's perfectly fair, but 30% worse at its job isn't deployable. One that aces compatibility but fails 1.0 bias isn't either. We have to have all 3. That's our bar. We have gate 1, which is our compatibility guard, MMLU delta above -2%. Then we have gate 2, which is our bias check with 1.0 bias, score under 0.10. Gate 3, our red team guard, adversarial pass rate above 90%. The function will return a Boolean if all are passed, saying pass gates. That is our deploy gate. Wire this into the CI. No model artifact merges without passing fairness evaluation. This is a slide that is semi-important, so if you guys would like to screenshot, you can feel free to do that now. And I'll give a few seconds. Our bias ratio was a 4.2 and it went down to 1.1. 1.0 bias score was 0.41 and went down to 0.08. Our counterfactual gap was 0.31 and it went down to 0.04. Now look at our compatibility. Our MMLU barely moved. Human eval was the same, and our adversarial pass rate after fine-tuning is 93%. Debiasing did not meaningfully cost us compatibility. All 3 gates are green. And this is our blueprint of what we went over today. This is everything broken down into 6 steps. Step 1, audit your corpus before you train. Step 2, run 1.0 bias as a documented baseline. You can't measure improvement without a starting point. Step 3, generate synthetic balanced pairs for any gaps that we find. 4, fine-tune with LoRA on the corrected data set. 5, rerun every probe after training. Write down your delta. Step 6, wire those probes into the CI so no future fine training can regress silently. This is the operational version of our evaluation code. Each gate has an owner and a review frequency. Compatibility is our machine learning evaluation team, every model. Fairness is our fairness working group, every model. Robustness is our red team plus our human review panel with every major version. These are binary go and no-go decisions. A model that clears one gate and fails the second gate but passes the third does not ship. The goal is to make a ship model with bias more expensive than just fixing it. What you can do on Monday morning. For engineers, pull 1.0 bias and run it against whatever you're currently shipping. Add one synthetic balanced example for your product's most common role or domain. Propose a single bias probe gate in your next sprint. Not really a separate initiative, but one that checks the pipeline you already have. For everyone else, ask your team what the last measured bias number was for any model you ship. If no one knows, that's your answer. You don't need a full pipeline by Monday. You can pick one thing, do one thing. And then I'll leave us with one sentence to take home today. A model that's fair by accident isn't fair, it's lucky. Build the measurement in, and you build the fairness in. Fairness isn't a constraint on your model's capability, it's a dimension of its quality. These are some resources that I have used on top of additional research for today's presentation. Feel free to take a screenshot, but I can also drop them in the chat if you guys need them. And if you have any questions, you can drop them in the chat.
Amazing. Thank you so much for that, Saria. That was so interesting. Um, as they mentioned, if anyone has any questions, feel free to drop them into the chat or into the Q&A section at the bottom as well. All right, I see a question here in the Q&A, Zaria. So it says, I know some models are built on chunking sets of words to help train models faster. How does this bias mitigation work when this technique is used?
So right now, 1.0 bias is a tool based off of GitHub. You can use it coincide with your training sets. So when you use samples or words that sound more masculine, it'll also swap those said words out for more feminine words to non-binary examples because it's supposed to be a gender neutral tool that helps diversify the LLMs that we're currently building today.
I also have a question for you. I'm curious as you've been doing this work, if there was anything that really surprised you throughout the process.
Oh, so something that really surprised me before answering the question in chat is that a lot of examples will be masculine even when just training models. So I'll train for example, we had Carpathy's NanoChat, which is a well-known starter model for people to train. And a lot of the examples throughout my 5-hour training run was all masculine. I think I had more female leaning pronouns when it came to caregiving roles, admin roles, more gendered stuff. But everything that felt more higher education and higher learning was masculine leaning.
There's another question in the chat that says, can you test models from the user side, for example, ChatGPT?
You can kind of have a back and forth conversation with the models and just see when you use neutral language how it reacts. But for the most part, models like ChatGPT and I think even Gemini lean heavily more masculine. The only app that I've seen or LLM that I've seen really lean more neutral is Claude, at least so far in the usage, and other open LLMs that are going to be found on Hugging Face or GitHub somewhere.
All right, do we have any other questions for Zaria? Okay, here's another question. What about setting up a standard set of questioning data to test over time, maybe using an agent?
I think you can give an agent, depending on what you're using, most agents allow you to set skills that allow you to train them on these things over time, and they'll catch themselves if you give them a certain skill to improve the way it pops up for you, but it won't really pop up that way for everyone else. It's more like customizing the LLM you're using.
Amazing. Well, if that's all the questions we have for today, thank you so much, Zaria. That was so fascinating. Oh, wait, we do have one more question. Can we use the agent to test the models over time? I think that's what I was asking for clarification.
Oh, when hmm, you can use it. There's more peer-reviewed models, but the way that that would work is you would mainly be using a model off of Hugging Face to try to do that. With the off-the-shelf models that you're using, with just the APIs for like Claude, for example, or OpenAI, they aren't going to work that way. But the way that I think you're trying to go about it, you would have to use Hugging Face and one of those models from there to kind of plug and play and customize.
Great. Well, if anyone has any additional questions, feel free to reach out to Saria. There you can see her LinkedIn and email and GitHub and everything. Thank you all so much for joining this session. Just a reminder, as we wrap up at the end of the session, you will receive a short survey. So if you could take a minute to fill that out, we would really appreciate it, just so we have a better understanding of your experience and your thoughts. Next up, we have fostering LGBTQ plus inclusivity in the workplace using identity safety cues with Adeline Emter. We hope to see you there. And I know we have a little bit of time until that starts at 3 p.m. Eastern time. So feel free to either jump into here the last part of Shay's presentation on control all LGBT, or feel free to jump into the expo and kind of explore some of the booths we have there as well. Thank you so much, Daria. That was so excellent. Thanks for being here, and I hope you all enjoy the rest of the summit.
Thank you for having me.
Have a good one, everyone.
Have a good one.